Yeah, welcome again. So for the second part of Newtonian gravity. So recall last time we had here the situation of two bodies A and B with masses capital M and small m attracting each other. And we had the Newtonian law. So we have that if you consider the motion of body B is attracted by A, so we have, concerning B, that from Newton's second law, his lex secunda force is mass times acceleration. We have m times xb double dot is minus g m over r squared times er. No? So this is from Newton's second law. Inserting in that law the gravitational force. Now actually this looks very innocent, but we have two different concepts of masses. So we have here in principle what we call an inertial mass, mi. So this is the mass that gives the resistance to acceleration and it has no gravitational origin per se, whereas this here comes from the gravitational law. So this we can call the mass mg, the gravitational mass, actually the passive gravitational mass, while this here, the capital M, is called the active gravitational mass, because this is the mass that attracts body B in this picture. No? So here, this here is mg, active. This is the one that enters Poisson's equation. I should write this down. So this is the inertial mass, and this is the mg, is the gravitational mass. So in German, this is träge Masse and schwere Masse. These are the words that Einstein himself used. Now, they are not independent, and the first thing is that the active gravitational mass must be the same as the passive gravitational mass. This is the trivial part of this in a sense, and it follows from the actio equals reactio law, because we can also view this as from the point of view of A, which is attracted towards B. No, so we have here first that the active gravitational mass is equal to the passive gravitational mass. No? So this follows from actio equals reactio, which is Newton's third law. Now why? Well, just write down this law from the point of view of B and then from the point of view of A. So we have mi xb. This is what you find here is minus g mg passive times mg active over r squared er, and it gives you the force that A exerts on B. No? B is attracted by A by the mass capital M. But you can also go to A, and then we have here mi times xa double dot, this minus g mg passive times mg active over r squared times er, or times minus er, sorry. Is in the other direction, of course. I mean, B goes in this direction and A goes, of course, in this direction. So you have here minus er, and this is F B on A. Now from Newton's third law, we know that F A on B must be the same as minus F B on A. So in order for this to hold for all possible masses, then it's clear that, these two must be the same, and also these two, which is the same, must be the same. You cannot have this for all possible masses if they were different. So we get that mg passive is mg active, which we call just mg, and mg passive is mg active, which we just call mg. Now, so we don't have actually to distinguish between passive and active gravitational mass, and we can just write then, I mean, for the first line we can just write mi xb double dot is minus g mg over r squared er, which is mg times g. So you see, Newtonian gravity is consistent for inertial mass and equal gravitational mass. You can build the whole edifice of Newtonian gravity on this, and you would not arrive at an inconsistency. Because like if you have electrostatics, say, or electrodynamics, I mean, you have here mi of a charge, but here you have the charge, and of course you have ratio E over m, which is depends on the particle. But the surprising feature is that all experimental evidence says that mi is equal to mg, which we have used already in the last lecture. So all experimental, and this is important, evidence so far indicates that mi is equal to mg. So inertial and gravitational mass are the same for all bodies. This was already known to Galileo and to Newton. They knew it from pendulum experiments, for example, accuracy of 10 to the minus 3. Now, today, this is known to an accuracy of at least 10 to the minus 13, but there are observations going on in satellites that extend this to minus 10 to the minus 15. The French experiment microscope reported 10 to the minus 15, and there are some suggestions that one could measure it up to 10 to the minus 18, but whether these projects are really realized is not clear at the moment. Now, when you have mi is equal to mg, then you see here you can of course cancel out the m, and you just have xb double dot is equal to g. No? And this is what we call the universality of free fall. No? So we have x double dot is g, so the universality of free fall. So all bodies fall with the same rate. The motion in the gravitational field is independent on the mass small m. Now this is also called the weak equivalence principle. Weak equivalence principle. This equivalence refers to the equivalence between gravity and inertia, and weak means this statement of the two concepts of masses are the same, which means that there are more, as you will see, more general notions of equivalence principle. So we use the acronym WEP for that. Now the weak equivalence principle, as I already said, is an isolated, unexplained fact in Newtonian gravity, but it lies at the heart of general relativity, and it was Einstein's genius to have recognized that out of this isolated fact that over 200 years no one really took much notice, that so that this is the key to a generalization of gravitational theory. He took this as a starting point for developing general relativity starting in 1907, and actually he generalized it. He assumed that not only this mi equals mg holds, but the dynamical laws are the same whether you are in a small enough freely falling system or in a gravitation-free space. So Einstein, 1907, okay, dynamical laws of physics in which he did not include the gravitational laws by themselves, but if you are in a freely falling system, you make, for example, electrodynamic measurements or measurements of atomic forces, then you cannot distinguish between free fall and gravitation-free space. So dynamical laws in a small, this will become later while we need here a restriction, freely falling system are equivalent to the laws in a gravity-free space. That is, if you have such a box, you cannot see outside, and it's floating in interstellar space, for example, and you just throw a body, then there's no gravity; it will just follow a straight line. There's no force, and this is the same or equivalent as if you are in gravity and you freely fall. Free fall. So here's no gravity, and then you also, if you throw a ball, the ball will continue to move on a straight line. So by no means inside that small box can you distinguish whether you are really freely falling or whether you are floating in interstellar space. And because this is a generalization of just the universality of free fall, because this does not make statements to, say, electrodynamic laws here inside, it's called the Einstein equivalence principle. The Einstein equivalence principle, or calling just EEP. And if we just talk about the equivalence principle without weak adding or Einstein, then we mean the Einstein equivalence principle. So that's for short the equivalence principle. For short, equivalence principle, EP. So if you just talk about that, this is what we mean. And you have here the equivalence between no gravity and free fall. The same holds for constant acceleration if you are on a rocket or if you stand on Earth. So if you have here, say, this box, you accelerate here with g, then you are here on your feet, and if you throw a ball, you have the usual parabola. So this is an accelerated system, so a rocket, and this is equivalent. So if you're here on Earth, and here you have this gravitational acceleration, and here you just stand here and throw your ball, as you know, if I could do when just throwing this piece of chalk. Now, this is something that holds locally. I mean, if I just have a box that is here freely falling, but what about, say, bigger systems? If I consider the whole Earth, and so this is the Earth, and I have various such boxes, then it's clear that these boxes all fall to the center of the Earth. So here we have a box that falls here, here we have a box that falls here, and here we have a box that falls here. Right? They're all freely falling. You don't feel any gravity in them, but so they are inertial systems in that sense, inertial, that, I mean, free bodies follow straight lines, but taken together they do not form one global inertial system. Because, as you see, because they are all moving towards the center of the Earth, they are relatively accelerated. So you don't have one global inertial system with all of them being in inertial motion. You only can realize this locally, because otherwise, I mean, if the Earth were absent, then of course any boxes which would be released parallelly would stay parallelly and would not go to the center of the Earth. So there's no global inertial system. So in the presence of gravity, no global inertial system can be realized. And this is what Einstein then led, and of course we will discuss this later, led the notion of a geometric description of gravity, because these things together, these local inertial systems, they do not fit together to one. And this is like if you have a curved surface and the local planes, they do not fit together to one global plane. The relative accelerations between these, they are called tidal accelerations. I mean, from the tidal forces, the moon that creates tidal forces on the oceans. And which means that here, if we have freely falling test bodies, and they originally say have a circular shape, if I have here a gravitational force, they will be distorted in an egg-like shape that will be more or less looking like that, because they are attracted more than this, and so on. So one can show that the area is preserved by that, but they will not retain the shape. Well, I mean here. Okay, so far for today. Then, I mean, in the exercises, you will have some example, or in the script, discussing the tidal forces of the moon on Earth. And maybe I can only indicate this here from Newtonian gravity. Of course, you can calculate the relative force between two really falling bodies. So if they are in a gravitational field, they attract each other, then you can not only, of course, you know what this is, but you can also have the acceleration of this orthogonal distance of that. So if I call this chi here of the two bodies, and they both freely fall here, then the Newtonian gravity, you get that the second derivative of this is minus the sum from j equals 1 to 3, and the second derivative of the gravitational potential at point xk times chi, and higher orders. I mean, this is from a Taylor expansion, if you assume they are infinitesimally neighbored. So you write down Newton's second law for this particle and Newton's second law for this particle, and then you expand this in the small distance. And so you have the vector that points to here is this plus this, and you expand in this small, and then you make the difference, and this is then what remains. It's the second derivative of this. And that's the law for the tidal forces, for the influence of the moon and the sun on the oceans, for example. And this is also what we will generalize in general relativity, and will lead us to notions such as the Riemann tensor. But this is far away. So far we have discussed Newtonian gravity, and so the next lecture will then be the first part on Einstein's special relativity, because this was the occasion on which he abandoned the absolute simultaneity of this Newtonian picture. And the special relativity also later gave him the idea of the four-dimensional space-time under the influence of Minkowski, so that he could generalize to the four-dimensional space-time of general relativity. So, thank you for your attention, and hope to see you. Well, I don't see you actually. Hope that you see me and watch me next time. Bye-bye.